I live in paradise, nestled on a plateau between the Jemez and Sangre de Cristo Mountains. The Rio Grande is right over there, 3 miles from my house. And if you were to go for a walk on the way to your favorite hiking trail, you might see two mothers with their strollers. You might think they're talking about mother things. And as you pass by, you'll hear, "But that Fourier transform clearly indicates." It's a science town full of scientists. It's Los Alamos, New Mexico, home of the historic Los Alamos National Lab. Our accelerator there smashes protons into a tungsten target at 800 MeV, shredding that tungsten into fractions of atoms, some of which are free neutrons that we harvest. They bind themselves in the cold embrace of cooled polyethylene, where they deposit most of their energy. They then encounter a solid deuterium crystal. You know, deuterium, a kind of hydrogen, but so cold it's solid. The neutrons come out of that crystal so cold that, well, I couldn't outrun them, but there are people who can. Like Usain Bolt, he would cream them in a race. And I am privileged enough to play with them. I belong to Caltech, but I'm on detached duty, stationed 1,000 miles away at this facility that turns tungsten into these free ultra-cold particles that we do experiments on. And why ultra-cold? Because this is how we're able to manipulate them. Their characteristic energy is on the order of the difference in potential energy as we pipe them up and down in gravity, comparable to the energy they gain or lose interacting with the magnetic field, so we can polarize them. And they see material surfaces. Ultra-cold neutrons, free neutrons that are so cold we can pipe them around like a gas, bottle them, manipulate them with magnetic fields. These free neutrons, sorry, I gotta slow down. They're unstable particles, so when we make them, we need to use them right away to probe the questions we're after. And my questions, my experiments, it's a collaboration of dozens of institutions united by this common goal of measuring the neutron's electric dipole moment. This same signature will explain the disparity of matter and antimatter of the universe. And it'll show itself in this tiny measurement that we want to measure 2 orders of magnitude better than anybody else. So you can imagine this science is really big. And I don't mean just the questions, though the questions we're looking at are mind-boggling. Why is the universe made of matter? I mean, when we make matter in an accelerator, it comes with equal parts antimatter. So where's all the antimatter gone? But I mean, the science, it's physically big. The accelerator is 3/4 of a mile long. The high bay where we do these experiments, it's 3 stories tall. And there are tons of people, 100 people in my experiment, several more hundreds in the accelerator complex. So I'm intraneutrons because of the largeness of the questions, the magnitude of the places we work, the size of our high bays, and the bustle of the accelerator complex as we all run around to do a little bit of everything. There's programming, there's data analysis, so programming in your scripted language of choice. There's building apparatus with your hands. There's taking data and babysitting the accelerator as beam smashes into tungsten to create those neutrons we desire. There's sitting here, right here, and writing my electrode paper before Brian says it's time to get started. So it used to be a little bit of everything. But right now I simulate, only, alone. My part in this endeavor currently is simulating and designing the electrodes that will allow us to put that high electric field across the neutron measurement cell. And when the world wakes up from coronavirus, I'll be ecstatically wrenching together the cryogenic system to test these electrodes that I've spent months only imagining in my simulation program. but I miss it. I miss real life. I miss wrenches. I miss running up and down the mezzanine because your cryogenic system is becoming unstable and might quench your superconducting magnets. I miss the accelerator beam where you're staring at the diagnostics at midnight, your adrenaline overruling your desire to sleep because you cannot waste this millions of dollars of beam on something like a segmentation fault or a sparking particle detector. You have to fix it and fix it now. And I miss my people and the bustle they bring. We can't do this alone. It's not a tabletop experiment. It's a high bay full of life and friends scattered all across the country that you fly around to, and they're excited to hear about your progress, and you're excited to actually see theirs. And they come here to Los Alamos to install their stuff too, to use those wrenches for themselves. Do you remember what that was like before the COVID struck? Big hollow tubes of metal that we cram into and teleport across vast quantities of space. I miss it. I've not adjusted to staying home and working on simulations only. I miss the real life of real neutrons bouncing along their guide tubes. Now I sit at home and simulate fake neutrons bouncing down fake guide tubes in the smallness of my townhouse, in the small screen of a computer, all alone, and simulate. But that's not enough for me. I'm an extrovert, an adventurer, and I'm an experimentalist. I need more.